Hey there, 10th grade chemistry students, and welcome to this definitive explainer. We're going to do something incredibly useful today. We're taking the modern periodic table, which, let's be honest, usually feels like an absolute nightmare of endless rote memorization, and we're going to prove that it's actually a beautifully predictable code. We are going to transform all those dense, overwhelming rules into an intuitive, memorable cheat sheet. Basically, think of this as your ultimate study guide for mastering periodic properties and how they change.
So let's just dive right in with the ultimate question, the one that really unlocks the entire periodic table for your exams. How can you predict exactly how an element is going to behave? Whether it'll react violently, form a basic salt, or just sit there completely inert, all by just looking at its unique address on a grid. When you're staring down a blank exam paper, that ability can honestly sound a bit like magic. But I promise you, it's pure, undeniable logic. Once you learn how to read the grid, the exam anxiety completely disappears because it just becomes a simple puzzle to solve.
Here's our roadmap for mastering the table today. We'll hit up the periodic map, dive into key periodic definitions, and uncover the engine behind the trends. Then we'll decode the atomic radius, check out the tug-of-war properties, and finally wrap the whole thing up with an ultimate summary table. All right, let's kick things off with part 1, the periodic map. We really need to get a solid grip on the structure of the grid we're working with. The foundation of our map is pretty straightforward. It consists of 18 vertical columns, which we call groups, and 7 horizontal rows, which are known as periods. Every single element is organized sequentially by an increasing atomic number, which is represented by the letter Z. And remember, that atomic number? That's the absolute DNA of the element. It simply tells you the exact number of protons sitting right there in the center of the atom's nucleus. It's never a fraction, always a whole number, and literally no two elements in the universe share the exact same one. Now, here's a massive clue for your exams. A row isn't just some arbitrary horizontal line. The period number actually tells you the exact number of electron shells a specific atom has. So, if an element sits in period 3, its outermost electrons are filling up the third shell. Down in period 6, it's got 6 shells. It's a direct, visible code for the atom's physical structure. Knowing this gives you an immediate mental picture of the exact atom you're dealing with.
Moving right along to part 2, key periodic definitions. Now that we know the map's layout, let's nail down the specific terminology you need to memorize.
Okay, here's the core vocabulary you absolutely have to drop in your written answers. Let's break it down so it's super easy to digest. First, the physical trait. Atomic radius. This is simply the atom's physical size, the distance from the dead center of the nucleus to the outermost electron shell. Next, the behavioral traits, metallic and non-metallic characters. These just describe an atom's willingness to either lose or gain electrons respectively. And finally, our 3 heavy-hitting energy terms. Electronegativity is the pulling power an atom exerts on shared electrons. Ionization potential is the sheer energy needed to physically rip an electron away from an atom. And electron affinity, that's the energy an atom happily releases when it grabs a brand new electron.
Which brings us to part 3, the engine behind the trends. We've got the map, we've got the vocabulary, so what's actually driving these properties to change?
To really make this stick, let's use a real-world analogy. The entire engine of the periodic table is basically a massive battle between 2 forces. As you go down a vertical group, you're continually adding new electron shells. Think of this exactly like putting on extra layers of chunky winter coats before stepping out into the snow. The atom just keeps getting physically larger, bulkier, and the outermost layers get further and further away from the center. But as you go across a horizontal period from left to right, you aren't adding any new coats. The shell number stays exactly the same. Instead, you're just adding more positive protons to the nucleus, increasing the nuclear charge. This acts exactly like pulling a belt tighter and tighter around your waist. That strong, growing positive center exerts a massive pull on those existing shells, pulling them inward and literally shrinking the atom down.
Let's cook that into practice with part 4, decoding atomic radius. We're going to apply our engine analogy right to the physical size of the atom.
When you get hit with one of those tricky 5-mark exam questions asking you to arrange a random jumble of elements by their atomic radius, you don't need to panic. You don't need to guess. You can confidently solve it by just applying the exact analogy we just talked about. Just remember our simple rule. Atomic size clearly increases as you move down a vertical group because you're piling on those thick winter coat layers of extra electron shells. But That size predictably decreases as you move across a period from left to right, because that tightening nuclear belt is pulling all the electrons much closer to the center. Honestly, if you lock this single foundational concept of coats versus belts into your mind right now, every single other chemical trend is going to naturally fall right into place. All right, part 5, the tug-of-war properties. It's super interesting how we can view the rest of the properties as a giant chemical game of tug-of-war.
If you need to figure out an element's chemical vibe, here's the secret. Metals want to let go of the rope. Because they're physically larger and bulkier, their outermost electrons are sitting far away from the nucleus, so they very easily just let go and lose them. Nonmetals, over on the right side of the table, are much smaller, with a really tight, powerful nuclear grip. They desperately want to pull the rope toward them to gain electrons and complete their set.
If we compare Group 1 alkali metals to Group 17 halogens, we perfectly see the dramatic extremes of this tug-of-war. Group 1 elements, way on the far left, are the ultimate losers, and I mean that chemically. They have just one lone electron in their outermost shell, and they are highly reactive because they want to toss it away to achieve stability. In fact, they're so desperate to toss that electron that dropping a chunk of pure sodium into a beaker of water causes a literal explosion. On the exact opposite side, Group 17 halogens are the ultimate gainers. They sit there with 7 valence electrons, pulling the rope incredibly hard to snatch just one more electron to reach a perfect 8. This aggressive pulling nature is exactly what makes them fantastic salt producers.
Let's tie this all up in part 6, the ultimate summary table. We've covered a ton of ground, from the grid itself to winter coats, tight belts, and explosive tugs of war. You're definitely going to want to save or screenshot this summary table for your revision. It neatly brings together every single trend we've talked about, and just look at how perfectly balanced this system is. As you go across a period left to right, the atom shrinks. Because it shrinks, it becomes way harder to lose electrons, meaning its metallic character goes down. But because of that tight nuclear grip, it becomes amazing at attracting new electrons. So non-metallic character, electronegativity, ionization potential, and electron affinity, they all increase in tandem. Conversely, as you move down a group, the atom becomes huge. It gets so large it can barely hold onto its own outer electrons, so its metallic character shoots up, while its ability to pull in any new electrons completely plummets. At the end of the day, when you're reviewing past paper worksheets and feeling lost in the weeds of the vocabulary, just remember this absolute core rule of chemistry. Atoms just want to be stable. They will gladly lose, gain, or share their electrons to achieve that perfect, highly stable configuration. Every single periodic trend we've discussed today is ultimately just a measurement of exactly how they go about getting that stability.
So, with this complete codebreaker guide locked in your mental toolkit, you're no longer just memorizing a static, boring chart. You're actively reading a map of atomic behavior. The next time you look at an element's unique address on the table, what secrets is it going to instantly reveal to you? Trust the foundational logic of these trends, use your cheat sheet, and you are absolutely going to ace those chemistry exams.